Okay, let's talk about an introduction to changes of variable. And if we can recall the 1D situation, if we have a definite integral of some function, then the idea is just you can use a u substitution of the form x equals, let's say, g of u. And what happens is the integration range is now it changes to u of a and u of b, where these are the u values associated with a and b, and now your f becomes g of u, and your dx, well, your dx becomes g prime of u du. Okay? And just to motivate what's coming, we're going to call this extra term here, the g prime, we're going to call that the Jacobian. And what it indicates is whether the volume, or really in this case the length, dx ratio, dx to du, whether it's greater than 1 or less than 1. So whether the transformation is expanding or contracting. And by the transformation, I mean the transformation from u to x. So let's just do, I think the most important example by far are rescalings. And what it is just it's linear g. And so really, for example, x equals 2u, or x equals, let's say, 1/2 u. Let me just do 1/3. So in this case, the transformation u to x is expanding, right? Because given a unit u interval, this transforms now to twice the length of the x interval. And similarly, this is a contracting, because the unit x interval, the unit u interval transforms to a smaller x interval. Okay, so in terms of our AB in x, this will now become, in the u space, let me just draw that over here, AB, this will now come from a over 2, b over 2, right? So that expanding map, it maps a smaller interval to a larger one. And conversely, if you start with a big x, it becomes a smaller u. And if you go the other way, 1/3, you actually now have 3a and 3b. That's right, these are your u's. And now these become ab and x. Because you start with a big u and you go to a small x. I'm just trying to give you some intuition about how these rescalings work, because a lot of times transformations are easier to visualize than they are to compute. So in this case, in the expanding case, the Jacobian dx du, it's equal to 2, and in this case, the Jacobian is equal to 1/3. Okay, so I'm just trying to give you some intuition about what this Jacobian represents. It represents whether we are expanding or contracting with our transformation. And I should note that, just so you don't get this, just so you don't make mistakes in the transformation, the Jacobian size is opposite to the new interval size. So for example, 2, as the Jacobian, it turns out our new interval in U space is half the size of the original interval. So to write this in words, we integrate 2 over 1/2 the size of the interval to get the original size. So reducing the size of the interval compensates for that 2. Okay? So why am I going through this? Because really something similar works in 2D and 3D and so on. Rescalings. So if we have let's just do over a rectangle. So if we have x equals a and b, y equals c and d, we'll integrate over this region R. Well, if we integrate from a to b and c to d, this will be our x, this will be our y, and we have f of x, y, dy, dx. What you can do is something very similar. You just let x equal, for example, 2u, and y equals, for example, 1/3 v. And this will, what this is you can think of this as a u substitution in two variables. And although now there's a v, so you don't call it a uv substitution, you just call it a change of variables. Can you imagine doing this in 3 dimensions and calling it a UVW substitution? I think change variables is more succinct. So what you do is just, as before, now you let dx equal 2 du and dy equal 1/3 dv. So that means dx dy equals 2 times 1/3 du dv. And now this thing, 2/3, is the Jacobian. And this is written as, in this form, it's really what it is a dx dy divided by du dv. And the notation that people use is you put x and y on top and u and v in the bottom. So, for example, if x and y are meters squared and u and v are, I don't know, centimeters squared, then the Jacobian would have units of the quotient of these two units. And the important thing is that it has meters on top. Maybe I shouldn't have used centimeters, maybe feet squared. So it's just, what I'm trying to say is you need to put the x's on top for the Jacobian because the left-hand side has x's. Okay? So if you do the substitution, in this case, u to x expands because the Jacobian is 2, and v to y contracts because the Jacobian is 1/3. So that means the original, or rather AB in x, it should contract, or it should come from something smaller because this has been an expansive transformation. So this should be from a over 2 to b over 2. Really what this is just u of a, u of b, in case you're confused about that. And similarly, CD, it should be the opposite of the Jacobian. So it should be 3c, 3d. And again, this is just v of c, v of d, in case you're confused about that. You just solve for v, or solve for u, and just plug a in. So solve for u, plug limits in. And similarly, solve for v in this case. But what I just did here was just argue in a kind of heuristic, quick way that you don't need math to think about. Okay. So once you do all that, and you just plug it in, so plug in the new limits and the Jacobian, what you get now is the new limits a over 2, b over 2, that's u, formerly x, and now you have 3c and 3d, that's v, formerly y, and now f, you plug in x and u, so 2u, 3v, and now you have dv du times the Jacobian, which in this case is 2/3. Yeah, and make sure not to miss this Jacobian term. It's essential. And I think it's probably one of the two difficult things about changing variables. The other is just changing the limits. I think this is I think this rescaling is one of two most important changes of variables. Rescalings, because and the other one is rotation, which we'll cover next. But the reason is that, like for example, in the let me just give you like a physical example. In the hydrogen atom, you often have the integrals of stuff involving constants. And so what rescaling allows you to do is to get rid of these constants. And so so if the integral has an a in here, you can actually predict from the outset that the integral will be of some form, c divided by a, where c is just some it's just some number, some explicit number. So I would say, so rescaling allows you to do half of the work already. Because if you know if it has a parametric dependence of 1 over a, for example, then that's already pretty good. And really just that number often in many applications is often not important. Okay, so next we'll move on to seeing how to use rescalings to evaluate integrals. Thanks for watching.